Hello. Today we are starting motion in 2 dimensions. So far we've been doing it in 1. Now we're moving to 2D. So it's considered 2D kinematics or 2-dimensional kinematics. Now, for convenience, we are going to say that any 2-dimensional motion is in the XY plane, regardless of whether the plane of motion is horizontal or vertical. So I'm about to draw a figure up here. And what it's going to show is a particle moving along a curved path, which is called a trajectory in that XY plane. And we're going to locate the particle in terms of its position vector. All right, so here we have the XY plane. And this black line right here is what we call our trajectory. All right. And this blue line right here is our position vector, okay? So let's say we're at this position. This would be our position vector. Now, what we call the position vector, how we represent it, is we call it R, vector R. And what vector R is equal to is X I hat plus Y J hat. Now this I hat and J hat are basically just other ways to say X and Y. Get used to seeing them. The I hat is always going to let you know it's in the X. The J hat's always going to let you know that it's in the Y, okay? So, just like we've been doing with our other vectors, we can break this position vector up into its components. So, bam, we're going to have its X component, and we're going to have its Y component. All right, so this right here would be represented as R sub X, which is also just going to be our X. And this over here would be R sub Y, which is Y. So those would be our 2 components of this position vector in regards to this trajectory. Now, the pink and green that I'm going to use, pink and green, all right, they're going to show the particle moving from position R1 to position R2 at a later time t sub 2. All right, so I'm going to clap my hands and make some magic happen. All right, so with this graph, we are going to be talking about the average velocity and how it's pointing in the direction of the displacement vector delta R, okay? So this right here would be our delta R. This is our displacement from 1 to 2. So our displacement from position 1 to position 2. And how our velocity works is that we are going to have an average velocity, okay? An average velocity, when we previously learned it, was delta X over delta T, right? But now we have a delta R. So our average velocity in 2D kinematics is delta R over delta T. So our change in R over our change in T, okay? Now, when we break that up into the components like we talked about previously, how we can break things up into our component vectors, it's going to be delta X over delta T I hat plus delta Y over delta T J hat, okay? Now, our average velocity, as it says, is going to point in the direction of the displacement. So, our average velocity would look like that, which is very, very light. So it would look like that, okay? It's going to go along that displacement vector, okay? And where our delta Y and delta X are going to come from are going to be the y and x components of this displacement vector. So this will be our x component, and this will be our y component. So this would be our delta y, and this would be our delta x, from breaking that up into its x and y components, okay? Displacement now, instead of being a final position minus an initial position, is going to be that delta r equals delta x I hat plus delta y j hat, okay? And then we also have to consider instantaneous velocity. So do you guys remember that last time when we talked about instantaneous velocity, we talked about how the limit of our delta t approaches 0 over the delta x over delta t? Well, now for our instantaneous velocity, which let's make this blue just so we can tell the difference. If we want the instantaneous velocity at a point, the limit as delta t approaches 0 of delta r over delta t, okay? That's how we find the instantaneous velocity. Now, if you remember correctly, that means that we do the derivative of position. So we're going to have dr over dt, which means that our instantaneous velocity is going to be the derivative of x over dt I hat plus dy over dt j hat, okay? Now remember once again that these I hats and j hats are just another way of saying that this is in the x or the y direction, okay? Now, if we put this all together, what we eventually get is just that v, that instantaneous velocity, is equal to the velocity in the x direction plus the velocity in the y direction. Because remember, if you're taking the derivative of position, that is indeed velocity, all right? And just like previously, instantaneous velocity is going to be tangent to the curve, okay? So if we wanted the instantaneous velocity at point 1, it would be right here, and it would be tangent to that curve. Okay, so let's talk about if the velocity vector has an angle theta measured from the positive x direction, okay? So that would be like, this is our velocity right here. This would be our x component of our velocity, and this would be our y component of the velocity. And when it says that the velocity vector's angle theta is measured from the positive x direction, it means that it would be right here. So this would be the theta that we were given, okay? Now, if that's the case, to find these components, you're going to have that Vx is equal to my personal favorite of V cosine theta, all right? And our y component is going to be equal to Vy equals V sine theta, okay? So the x component is V cosine theta, the y component would be V sine theta, where the speed at that point, which would just be V, our magnitude, is equal to the square root of, you guessed it, Vx squared plus Vy squared. Just like we've already been doing with vectors in class. The x and y components, when you add them together, do the Pythagorean theorem, you find your hypotenuse, okay? And remember, that is the speed. There's no direction with that. That's just the speed. It's only magnitude. If you want the direction, what you're going to do is you're going to say that the theta is equal to the inverse tangent of Vy over Vx, okay? So let's just tell you one more time. If the angle theta is measured from the positive x direction, the velocity vector components are Vx equals V cosine theta and Vy equals V sine theta, and our theta or our direction can be derived by the inverse tangent of Vy over Vx. So let's do a quick little example together. Okay, so finding velocity. We've got a sports car, and its position on a winding road is given by the following function. We have that vector r equals 6.0t minus 0.10t squared plus 0.00048t cubed I hat plus 8.0t plus 0.060t squared minus 0.00095t cubed j hat. Okay, so that is a long function, and that is our vector r. Okay, and it says where the y-axis points north, which means it's going to be positive, t is in seconds and r is in meters. What are the car's speed and direction? So that would be its velocity, because you want speed and direction. So what is velocity at t equals 120 seconds? Okay, now we just talked about how an instantaneous velocity, Vx, is the derivative of x with respect to t, and Vy is going to be the derivative of the y with respect to t, which means we need to take the derivatives of these two. So this first one, if we take the derivative, remember, it's going to be, you bring it the n down, multiply it, and then it's going to be t to the n minus 1. So what's going to happen here is it's going to be 6.0 minus 2 times 0.10t plus 3 times 0.00048t squared, okay? And then for this one, it's going to be 8.0 plus 2 times 0.060t minus 3 times 0.00095t squared. All right, so we now have the components of this vector. We have the velocity components of this position vector, all right? From there, we now need to plug in the 120 seconds, okay? Because remember, if we just do this, we get that that's the I hat plus this right here, which is the j hat. So we're going to need to plug in 120 to each of these t's, all right? So when we do that, when we plug in 120, we get that vector v, our instantaneous velocity, is equal to 2.74 I hat minus 18.64 j hat meters per second. So that is our instantaneous velocity. However, we need to find the speed and direction of this car, right? So what we're going to do to just find v is we're going to do the square root of the x component, 2.74 squared, plus the y component, negative 18.64 squared. Now, when we do that, we are going to get that the speed is 18.84 meters per second. And that's our speed. However, we want velocity. So we need speed and direction, okay? So remember, how we find that is we say that theta is equal to the inverse tangent of y over x. And remember, when we're doing this, we're always going to use the absolute values of the numbers. So 18.64 over 2.74, all right? So that should give you an angle of 82 degrees. And from looking at this where it has a positive x and a negative y, we know that this is going to be 82 degrees south of east, okay? So overall, what our velocity is 18.84 meters per second, 82 degrees south of east. All right, let's move on. All right, so until now, we were only talking about acceleration really as a change in its speed. So maybe your acceleration was negative 50 meters per second squared, and then it changes to negative 40 meters per second squared, or something like that, right? However, isn't acceleration the change in velocity divided by the change in time? And velocity doesn't only change by magnitude, which would be speed, it also changes by direction. So acceleration doesn't only change when the speed changes, it also changes when the direction changes, okay? So let's talk about different steps to finding an acceleration vector, okay? So let's say we're given these two vectors. This is our initial velocity and this is our final velocity. So the first thing we're going to want to do is we're just going to want to draw that final velocity vector. So I'm going to draw it off to the side here, and that is our final velocity vector. The next thing we're going to want to do is draw negative v naught at the tip of the f, okay? The tip is the arrow. All that happens when we do negative v naught is now it's going in the other direction. So instead of the arrow going down, it'll be going up. So if we do that, we will have now a negative v naught tip to tail with that final velocity. Now, in order to draw a change in the velocity, we should know that that is vf minus v naught, right? So what we're going to have now, and what we see here, is basically just vf plus negative v naught. So that is why we had to make this negative v naught there, okay? So in order to find that, we're going to put the resultant vector, okay? That's going to be our change in v, because that is vf minus v naught. From there, you're supposed to return to the original motion diagram that you were given and draw a vector at the middle point in the direction that the change in velocity takes place. Because this change in velocity direction is going to be the direction of our acceleration. So if I try to line that up halfway decently, this would be my acceleration vector. So the direction of the acceleration vector is going to be the same direction as your change in velocity, which makes sense because acceleration is change in velocity divided by change in time. time doesn't really have a direction, does it? So it's going to be in the direction of that change in velocity, okay? So let's do another quick little example together. This one is mainly going to be conceptual, okay? What we have is a ball, okay? And it's going to roll down a hill through the valley and back up to the other side. And we want to draw a motion diagram showing how the velocity and acceleration react during this time. So let's start out by just drawing what that would look like. So if the ball starts up here, then it goes down into the valley and comes back up. That was a horrible drawing. It is so hard to get these symmetrical. You know what? We'll say that's good enough, okay? So we have the ball and it's starting up here, and I'm going to drop it, and it's going to go down and come back up, okay? So when it starts here, let's start by drawing its velocity. So it's going to start out from rest, and it's going to go slow. And as it goes further down, what we're going to notice is that the velocity is actually going to pick up and get decently fast. Okay? And then it's going to end up at the bottom. Once it ends up at the bottom, what's going to happen is that it's going to start, do you think it's going to speed up or slow down as it goes up? Spoiler alert, it's going to slow down, okay? Because once it gets to the top, what ends up happening? It stops and it comes right back down, correct? So these would be our velocity vectors the entire way. But let's talk about our acceleration vectors, okay? So acceleration, it's going to be sort of going with everything for a while, right? Like it's going with it. Okay, well now it's starting to slowly experience some sort of change in direction. And then finally, all the acceleration is considered to be this route. This is telling you that there is a change in direction. When there is acceleration perpendicular, that means change in direction, okay? Now, this entire time it was getting faster and faster and faster, right? But now it's slowing down. So now our acceleration vectors are going to need to go in the opposite direction. They'll go against it, okay? Because what the acceleration is doing now is it's working to slow the ball down as it reaches the top of this path, okay? So an acceleration vector itself can actually be decomposed into component parallel, like components that are parallel to the velocity and components that are perpendicular to the velocity, okay? So if it's parallel to the velocity, that means it's changing speed, and when it's perpendicular, it's changing direction. So you see how it's parallel, 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 it's starting to get a little bit perpendicular, fully perpendicular. So all right here, you can tell that all it's changing is the speed. And then when you hit right here and it's perpendicular, you know for a fact that there has been a change in direction that has occurred. All right, we are back to the same trajectory drawing. So what I want to do here is sort of show you all of the different ways that we can actually break up acceleration vectors and then talk about what's actually the best way to do it. So let's say that this blue one, this is our acceleration vector, okay? So what we just looked at with the ball going up and down, right, was that it can be broken up into when it's parallel with the velocity and when it is perpendicular to the velocity. So we'll show that in green, all right? So here it would be perpendicular to the velocity, right? And here it would be parallel to the velocity, okay? However, this vector also has x and y components, which honestly, you know, this parallel and this perpendicular, it conveys very important ideas about acceleration, but using the x and y is just far more practical. So we would have the x component of acceleration, and we would have the y component of acceleration. All right, and those are going to be our more practical uses here, okay? We want to use that x and y component of the acceleration. Far more mathematically convenient, okay? Now, let's talk about how we would find that acceleration mathematically though, okay? Just like we did with velocity. We found out that to find that velocity, that it's equal to Vx I hat plus Vy j hat, right? Well, acceleration similar. To find our acceleration, it's going to be Ax I hat plus Ay j hat. However, acceleration is the derivative of velocity, isn't it? So, if we break this up further, we will get that acceleration is equal to the derivative of the x component of velocity with respect to t plus the derivative of the y component of velocity with respect to t. Okay? That means that our ax component is equal to dv sub x over dt, and our y component is going to be equal to dv sub y over dt. So it's just the derivative of velocity like we've always known. And what's really cool is that if your acceleration is constant, like it pretty much has been the entire time we've been talking about it, everything you learned previously is still going to apply. So consider a particle that moves with constant acceleration from an initial position of r naught equals x naught I hat plus y naught j hat, okay? That's going to be our initial position, starting with an initial velocity of Vx I hat plus Vy j hat, okay? Now, its position and final velocity at that point r, and these are going to look very, very familiar to you, okay, are going to be xf equals x naught plus v naught x t plus 1/2 ax t squared, okay? So the only difference right now is that we now have x's, okay? Then it would be yf equals y naught plus v naught yt plus 1/2 ayt squared, okay? And then for our velocity, it's going to be vfx equals v naught x plus axt, and vfy equals v naught y plus ayt. So you're going to have all the same kinematic equations, but now you need to make sure to have a sub x or a sub y depending on which part of the plane you're working in, okay? There are a lot of quantities to keep track of in 2D kinematics, so making the pictorial representation is all the more important, okay? So drawing pictures, way more important now. We will look at an example in class tomorrow when you get in, but I'm going to go ahead and give it to you, and I want you to try to work through it on your own before you come, okay? What I am leaving you with is plotting a spacecraft trajectory, all right? In the distant future, a small spacecraft is drifting north through the galaxy at 680 meters per second. When it receives a command to return to the starship, the pilot rotates the spacecraft until the nose is pointed 25 degrees north of east. then engages the ion engine. The spacecraft accelerates at 75 meters per second squared. Plot the spacecraft's trajectory for the first 20 seconds, okay? So I need you to plot that spacecraft's trajectory for the first 20 seconds. All you're gonna need to use is the equations for XF and YF and see what you can come up with, okay? Have fun with that, try it out, bring your work to class tomorrow, and it'll be the very first thing we do, and then you will get to start your problem set. All right, you guys, I hope you have a great day. Bye.